In this video, I'll go through the process of identifying whether a substance was oxidized or reduced in a redox reaction. So redox reactions are reactions that involve oxidation and reduction. Oxidation represents the loss of electrons. Reduction represents a gain in electrons. In order to determine whether or not oxidation or reduction took place, you have to compare the oxidation states of the atoms before and after the reaction occurred. You can think of oxidation states as being charges. They are similar, but not exactly the same. In order to identify the oxidation states, there are a few rules. One, whatever the charge is of an atom, it's going to equal the oxidation state, or the oxidation number. So when you see an atom by itself, that means that it's overall neutrally charged, and so that zero charge also represents an oxidation number of 0 for that atom. All naturally occurring molecules, as well as diatomic molecules, will have an oxidation state of 0. So recall there are 7 diatomic molecules, and they naturally exist as molecules containing identical atoms. Those molecules are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. If you're dealing with an ion, so a monatomic ion, so a single atom that has an overall charge, again, that charge is also the oxidation number. It gets a little trickier when you're dealing with compounds. Whenever you have a compound, you're going to have positive and negative. The positive is going to be the least electronegative. The negative is going to be the more electronegative. And so keeping those things in mind, it'll help in identifying the oxidation numbers to determine whether or not a substance was oxidized or reduced. Some other little tips that you'll see for your group 1A. So those metals, they will always have an oxidation number of 1. Same thing with group 2A. They're going to have an oxidation number of plus 2. I should have said a plus 1 instead of just 1. And so when you keep this in mind as you go through the rules, you'll start being able to identify and start noticing some patterns as you're determining what was oxidized and what was reduced. So if we look at the reaction shown. So in order to determine oxidation and reduction, we need to compare oxidation numbers before and after the reaction took place. One thing about reactions, especially when trying to identify oxidation numbers, the coefficients, they will not affect your oxidation number. So I can just erase those if I wanted to. I can get rid of them. They're not going to change your oxidation numbers. Another thing that will not affect your oxidation numbers, the physical states. So I can get rid of those as well. So whether or not a substance is a solid or a liquid or a gas or even in the aqueous phase will not matter. What we need are what atoms and how many of each are present. So we have that. Here we have iron plus oxygen to form iron 3 oxide. If you can name the ionic compound, it's going to give you clues about the oxidation number. So let's look at this particular reaction. We have iron, which is by itself. I don't see a positive charge to indicate that it's an ion, so I know it's an atom. Atoms are neutrally charged, so this will have an oxidation number of 0. I have oxygen. So although there are 2 oxygen atoms, remember oxygen was one of those diatomic molecules. So the oxygen would also have an oxidation number of 0. So we've taken care of both reactants. But then you have your products. Iron 3 oxide. Anytime you have a compound, you're going to have a positive and negative. Remember, compounds involve different atoms. And so one atom will be positive, one atom will be negative. In order to identify which one is positive or negative, look at electronegativities. So remember, electronegativity deals with the ability to attract electrons. Fluorine is the most electronegative atom, so the closer those atoms get to fluorine, the more electronegative they become. Nonmetals are more electronegative than metals. So we have iron and we have oxygen in a compound. The oxygen is more electronegative than the iron, so the oxygen is going to have my negative, meaning that the iron would have my positive. Now you have that formula, Fe2O3. Another tip is that oxygen will almost always be -2. The only time oxygen does not have an oxidation number of -2 is if you have a peroxide. In that case, the oxygen is -1. Other cases, it's -2. So in this case, we have the oxygen, so that's telling me my oxygen is going to be -2. Now, one thing that you want to remember, when you are looking at these oxidation numbers, so that -2, that applies to each individual atom in that compound. There are 3 oxygen atoms, so it may be helpful to write that -2 3 times. That way you'll remember that each oxygen is -2. So when I look at this particular compound and I factor in all of those oxygen atoms and the fact that each one has an oxidation state of -2, that means that the total negative of this compound is -6. Another thing with compounds, when you add the oxidation numbers of all of the atoms involved, those oxidation numbers must equal that overall charge. Compounds are neutrally charged, so an overall charge of 0. So what this means is that when I add in those 2 iron with these 3 oxygen, they should add up to equal 0. So I need to figure out what is the oxidation number of those 2 iron. So I'm going to just write it as 2Fe. If you want to write it as 2X, you can do that as well. I had 3 oxygen. Each oxygen was -2. When I add all these together, they're going to combine to equal 0. So from there, I need to solve this expression. So I still have my 2Fe. 3 times -2 is -6. So I can simply show it as -6. Instead of plus or negative, I just made it -6. Then I have still equals 0. Now I need to add 6 to both sides because I need that Fe by itself. Adding 6 to the left side causes it to cancel out. So on my left side, I simply have 2Fe. On my right side, I now have +6. But I need to figure out the oxidation number for each iron. Right now, 2 iron have an oxidation number of +6. To figure out for each one, I have to divide both sides by 2. So it cancels out on the left side to leave me with simply my iron. On the right side, it gives me a +3. So what that tells me is that each iron in this molecule has an oxidation number of +3. Again, you can write it twice if that helps. That way you can see that your total positive is a +6, your total negative is a -6. So you have all of your oxidation numbers. You have your oxidation number for the iron before and after the reaction took place. So it started out at 0, ended up at +3. Again, we're looking at an individual atom. Same thing with oxygen. Started out in a diatomic molecule with an oxidation number of 0, ended up in a compound with an oxidation number of -2. So one went from an oxidation number of 0 to a +3, the other went from 0 to -2. How the oxidation number changes will determine whether or not it was oxidized or reduced. One way, a little trick that I typically show, you learned about number lines many years ago. Write a number line. These reactions, oxidation and reduction reactions, are often referred to as redox reactions. Above that number line, write redox. Redox simply represents reduction and oxidation. Use this number line, Compare the oxidation numbers before and after to determine whether or not the substance was oxidized or reduced. So what do I mean by that? So if I look at the iron, the oxidation number of iron started out at 0, but then it ended up at +3. So if I'm starting out at 0, and so up under this little tick mark, I just show where I'm starting. So for this one, it starts at 0. In order to get to a +3 in a number line, you would have to go to the right to get to that +3. Going to the right represents oxidation. So this iron underwent oxidation, or you could say it was oxidized. It lost electrons. Remember, electrons are negatively charged. So by losing negativity, it became more positive. We can do the same thing with the oxygen. The oxygen started at 0, but then it went to a -2. In order to get to -2, I would have to go to the left until I reach -2. To the left represents reduction. So the oxygen underwent reduction, or you can say that it was reduced. Reduction indicates the gain of electrons. Again, electrons are negatively charged, so if this atom gained electrons, it became more negative, which we do see going from 0 to -2. So the little trick is using that number line, writing redox above, then looking at where the oxidation number started and where it ended to determine whether or not oxidation or reduction took place.